All right, let's take care of problem one on gas laws. All right. Now, as you've noticed watching the notes videos, there's lots of variables that we got to take care of, and there's lots of equations. But through these, I'm going to try to simplify how to think about and how to use it before you maybe try out some practice problems, or maybe you're comfortable and you just want to get right into the problems that you're assigned to do. But either way, we can go through some practice problems together. But if we're reading this, see, a 40-liter tank had nitrogen gas, N2, in it at a pressure of 113 kilopascals. If the pressure was dropped to 750 millimeters mercury, what would the new volume be? All right, so as we're looking at this, these are a little bit different than most problems that we've done this year. We have equations, which we typically don't have, and I haven't had you do this, but this is kind of a combination of physics and chemistry. Really, we want to write down what we have, write down our knowns and our unknowns, more than just dimensional analysis. Dimensional analysis really won't work here. And so we're going to write down what we know, and then we're going to try to figure out what equation we have is going to work, right? So the first one, I'm going to write a V, and I'm going to write that is 40.0 liters, okay? And then I'm going to keep reading nitrogen gas. That may or may not be important depending on the problem. And it says, all right, I got a pressure. I have a pressure of 113 kilopascals. All right, if the pressure was to drop to 750 millimeters mercury, now that seems weird because 750 is a bigger number, but they're two different units, right? And so we got to take care of that. So if we have a second pressure, so now I'm going to write a P2, and I went back up and I wrote P1s on them. I didn't know that I needed that right away, depending on the problem. But if this is 750 millimeters mercury, right? Just as we've always done in the past, we cannot divide, multiply, add those two. If they're both pressures, we have to have them in the same units, right? And so we need to take one of them. It doesn't matter which one, and we need to convert it to the other. And if you go to your notes, if you took good notes, or you might have to go back to that slide, there's that, maybe the third or fourth slide, where it's got all of those pressure units. And so this is where dimensional analysis is going to help us a little bit, right? We need to have millimeters mercury on the bottom, and we need to have kilopascals on top. And all we have to do is take those numbers from that page and put them here. So millimeters mercury at 1 atm, and we don't care about the atms, but that's what they're all equal to, is 760, and kilopascals is 101.3, and it might be 2.5, but 4 sig figs in this case is enough. Okay. So when we do that, all of a sudden we end up with millimeters mercury cancel. We have 750 times 101.3 divided by 760, and we get 99.97 kilopascals, right? So you can see where the drop came in, because this was actually dropped. So it should make sense when we do our math, and that's why I wrote the problem that way, just so you can see that. And then it says, what would the new volume be? All right, so then we have this new V2, and we go from there. All right, so that's kind of the first step. You got to be able to go through the steps that way. So then we're looking, okay, what problem or what equation that we've written goes through all of those variables? It'd be Boyle's law, right? So Boyle's law says this: V1 P1 is equal to V2 P2. All right. What I like to do at this point, because numbers always work out, right? You can put them in your calculator, and they always come up with an answer. And if you don't really know what you're looking at, if you don't really know what you're talking about, you don't know for sure if you're going to be right. So before I ever get into actually putting the numbers into the problem, I like solving for the one I don't know, right? So I'm trying to solve for that guy. You know how to do this. So V2 is going to be equal to V1, V1 P1 over P2, right? And it should make sense, because now those pressure units are going to cancel each other out, and you're left with a volume unit. Perfect. If we write it this way, now we can toss in our numbers, right? So my V1 is, if I have it up there, is 40 liters, right? And that's going to be times my P1, which is 113 kilopascals. And then my P2 is 99.97 kilopascals. And if I look at this, kilopascals cancel. I'm left with liters, which is good because that's what my V2 has to be. So putting that into our equation, we end up with 40 times 113 divided by 99.97. And we come up with a volume, right? So this is kind of be like our step 3 or 4. All right, our new volume would be 45.2 liters. All right, now we could do that same problem, and this is what I kind of alluded to before. You could memorize Boyle's law and Charles' law and the Gay-Lussac law, but honestly, if you knew the combined gas law, you could have still done this problem. So I'm going to take this one step further and show you we get the same answer. And that's the one you really have to know. It'll seem like a little bit of work, but it's probably better than trying to memorize all of the other ones. So the combined gas law is V1, P1, T1 is equal to V2, P2, T2, right? Well, you're probably saying, well, we don't have any T's. Perfect. Just make up a number. As long as the number is not 0, you're going to be fine, right? It can be any constant, right? It can be any constant. So we could say 100 Kelvin. And it won't matter because if we're still solving for V2, and I won't go through all the math, but I will show it to you. If we're still solving for V2, V2 is going to equal V1, P1, T1, right? That part hasn't changed. So T2 is going to go to the top and P2 is going to come to the bottom, right? Well, if the temperature was constant, that's going to be 100 Kelvin. That's going to be 100 Kelvin. So literally they're going to cancel each other out. The pressure units, right now, all of a sudden, it looks exactly like the problem we just did there. Exactly. So what I'm saying is we have all those individual laws they make it probably slightly easier as you're going through it. But the combined gas law, when you have multiple units, so you have multiple pressure units and multiple volume units, that's really going to get you generally where you need to go. So think about that.